I would take you through a little bit of atmospheric chemistry, and some of you have seen the slides and you said, wow, there's a lot of equations and difficult stuff in there. Don't get scared away by that. I'm going to fly gently over that, but I thought it would be interesting for you to just hear something different. I think I've already learned an incredible amount of stuff as an atmospheric chemist coming into this community. And I think there's a lot for chemists to do in the field of anesthesiology and really the mechanism of how these compounds really work. So it's been wonderful. So my plan is to give you a little bit of background for why we did this, the experimental methods, some results, discussion of the environmental implications, and some conclusions. And this study came underway by the normal way in science, by accident. My former student, his wife was giving birth and needed anesthesia. And being a chemist, my former student asked, what is actually in the mask? And then he was presented with names like sevoflurane and isoflurane and enflurane, and he went home and looked up what these compounds really were, and it turned out that they were halogenated ethers. And we investigated a lot of halogenated ethers for other applications for a company called 3M. So it can be used as heat fluids and isolators and solvents and God knows what as replacements for CFC compounds, for ozone depleting. So we kind of said to ourselves, well, you know, this is not going to be rocket science, but it would be kind of fun to see what has been done on the atmospheric chemistry of these compounds. And as it turned out, because health and doctors are such important things in daily life, this has actually been the study of all the studies that we have done. This has been the study that has received the most press. The results were in every single newspaper in Denmark and on more than 300 websites, including Discovery and Science and CNN and some even all the way to Vietnam. So we were quite surprised by this, you know, not rocket science study making the press like that. So it was an interesting experience. Now, getting further into the point here, when we emit things to the atmosphere, there are 4 general concerns that you don't think about them normally, but well, we think about them. And you could group them as radiative forcing, what you guys call climate change, stratospheric ozone depletion, which was what got me into this subject because this was discovered in 1974, and I was a first-year chemistry student at the University of Copenhagen, and I decided I wanted to save the world from this, and has been trying to do so ever since, naively. Then there is tropospheric oxidant formation. You guys normally know this as photochemical smog, mostly pronounced in the Los Angeles areas and other big cities. And then, you know, you can release stuff that is either harmful by itself or the degradation products can be harmful. So those are the 4 general concerns when we emit stuff to the atmosphere. And when we then want to do something about it, we want to do it based on facts. And you could ask the question, how do the anesthetics perform in these 4 categories, and how do we actually find out? And it's very simple. The way to find out is to know exactly what happens to them out in the atmosphere. So we need to know the atmospheric chemistry of these compounds. So just before we get into the matter, just to make you aware, then when we talk about climate change, here's a famous plot from the now old IPCC report 2007. It gives you a picture of the radiative forcing, the effect of different forces to the atmosphere since pre-industrial time. And, you know, CO2 is what everybody talks about, and that has a pretty pronounced effect measured in watts per square meter, 1.66, with a fairly low uncertainty. What most people don't realize is that methane, nitrous oxide, and halocarbons, they together have an effect, or has had an effect that is almost equivalent to that of CO2. And remarkably, you know, the yellow square here is my field, and, you know, those are all man-made, and they could all have been avoided if, you know, we had known better at the time when we started using them. So I think this is quite remarkable and something I would really like to leave you with. So, getting further, isoflurane, desflurane, and sevoflurane, they are halogenated organic compounds, and they're used in general anesthesia. The oxidation mechanism of those 2 compounds had never been studied when we looked at them first, and we wanted to take a further look on the global warming potential that were not well established. The annual emissions are quite unknown, and this is a number where you guys will probably have to correct me. This is from my doctor friends at the University Hospital in Ann Arbor, University of Michigan Hospital. They say about 200 million procedures a year. I don't know how accurate that is. You can educate me on that. So the goal of our study was to improve the understanding of the atmospheric chemistry of these compounds. And we will do that by establishing the kinetics of the reactions with chlorine atoms and OH radicals, establishing the oxidation mechanism, and then calculate the environmental impact or estimate the environmental impact. And how do we do this? Well, we used what is called a smog chamber or an environmental chamber. It consists of 4 parts. It consists of a container, so a glass, a Pyrex tube, big Pyrex tube, 100 liter or 140 liters, or a quartz tube. We have some vacuum lines to put gases into the system. There are some black lamps around here, which is the lamps that you guys will know from, in Danish we call it solarium. So this is places where you go to get suntanned. You shouldn't do that, but some people like to do it. We use this as imitating the sun. And then we have a Fourier transform infrared spectrometer to detect what is happening in the cell when we turn on and off the lights. And then, of course, there's a personal computer, as always, to manage the whole thing. So this was the schematic. In reality, it looks like this. I mean, it's not open when we have the lights on, because then you get too much suntan, actually. But this is just to show you. This is my picture. This is a professional picture of one of the co-workers. So sun lamps, the reactor, the vacuum line, and the spectrometer is behind here with the computer. So 140 liter Pyrex chamber. We do kinetics in this chamber, so we measure reactions with OH radicals and chlorine atoms. We measure infrared spectra and the radiative efficiency and calculate the global warming potential. It's in principle, very, very easy. If you want to study chlorine atom reactions, we put molecular chlorine in there, turn on the lights, and you produce chlorine atoms, and they react with whatever compounds we have in there. Making OH radicals, which is the important part for the atmosphere, is slightly more difficult, but it's for a chemist, it's only 3 reactions to make it, so that's fine. So that's how we do it. So we do chlorine kinetics, OH kinetics, oxidation mechanisms, and then IR, infrared spectra, and global warming potentials. And very quickly, and don't get bothered by this, fairly simple, we put the anesthetic compound in the chamber together with a compound where we know the reactivity with chlorine or OH. Then we turn on the lights, the reactions go, and we measure one relative to the other. So if we know the reactivity of the reference compound from the way the compounds decrease in the chamber every time we turn the lights on, we can calculate a rate constant for the reaction of chlorine with the unknown compound, in this case the anesthetic. And when we do that, so every dot is a measurement, you get nice straight lines, and this is the relative reactivity, and with some math you can get a rate constant. And I know these numbers are not going to mean anything to you, and it doesn't matter, and forget about the units. So we take the 3 anesthetic compounds down here, and 2 of them react at about the same rate, and one is faster than the other. And then as a chemist, you look at the molecular formula of these compounds, and you can see that isoflurane is different from the others, having a chlorine atom here. And actually substituting a fluorine with a chlorine, in my field of chemistry, it's well known that the hydrogen right here becomes much easier to abstract for the chlorine atom. So it should be faster. So this kind of confirms what an atmospheric chemist would intuitively expect. So this is kind of nice. And there had actually been some measurements of this rate constant, and what we do in my field is we compare to what other people have done, and you can see here that we all kind of pretty much agree. We also agree here, and here there was nothing to compare with. So that's fine. We have to remember that chlorine atoms is not the primary atmospheric loss process, so we need to look at OH. Here's very quickly, this is OH with sevoflurane. We measure it relative to acetylene and ethylene, and we do 2 references just to be sure, and then we get a number. And here we actually have 2 numbers, previous published numbers to compare with, that were in disagreement, and we seem to favor in this case the lower value of those previous measurements. And this is the major. Outside your window, you can't see it, but trust me, what takes anesthetic compounds out of the atmosphere is reaction with OH radicals. So this is the major pathway of getting rid of your anesthetic compounds in the atmosphere. So measuring the OH rate constants means that we can actually calculate a lifetime in the atmosphere for this compound, and this turns, in this case, out to be about 1.3 years with a certain amount of uncertainty. So that was the kinetics. So we know how fast these compounds are going away when we release them to the atmosphere. What comes out of this whole reaction sequence after the OH radical reactions? Well, the experiment is done in this way, that we fill the cell with the anesthetic compound and chlorine to have chlorine reactions, and then we switch on the lights for like 5 seconds. And then we take a new spectrum after we have had the reactions going on. And you don't have to be an atmospheric scientist to see that there's a difference between these two. So here something came up, and you can also see that some of the initial anesthetic disappeared. So we have had the initial, so this is like a fingerprint of the compound. So we have had the initial compound go down, and we have had new compounds come up. And when you know a little bit about, so this is what the products look like. And because we have done so many studies, we kind of know what products to expect, and we have reference spectra of those compounds. So we expect this peculiar compound, we expect formal fluoride, COF2, and you can see, especially if you're in the front row, that there's a little bit of that right here, so we can kind of quantify that. This one is pretty obvious that that's in there. So you can subtract that and actually quantify how much of each product is there. And you're left with something that we didn't know when we did this study, but we could kind of figure out what it was, and we could theoretically calculate the spectra. And it turns out to be what is called a fluorinated ester compound, which is the residual of that. So we could pretty much tell what is going to go on with this compound when you release it to the atmosphere. So this was desflurane. And when you put it into, in a chemical degradation scheme, it looks like this. So this is your original compound. It has 2 different hydrogens to abstract. So you can go down this way, or you can go down that way. And I've indicated the compounds that we can actually measure. We can't measure the intermediates because they're short-lived, but we measure the end products. We did the same for sevoflurane, so before radiation, after radiation, the products. And here, actually, my student did this because I didn't know how to do it. He or she drew the line, so you can actually kind of follow where the different absorptions are. Very nice. And we have identified the products again, and we can do that as a function of concentration to make sure that nothing, spectacular or unwanted is happening in the chamber. And we can do the same thing for fluorane. We identify the products, and we know what's going to happen to it when we release it to the atmosphere. So finally, the IR spectra. So the infrared spectra is what's going to determine one part of the global warming potential is going to be the infrared spectra. So we take a spectrum, a calibrated spectrum of each anesthetic, and we put it on an absolute scale. So this is an absolute absorption. And then we integrate that over this area. So we get something that is called the integrated absorption cross-section of the molecule. And then we have to think a little bit about the atmosphere. So this is how the atmosphere looks from top of, when you look from the outside into the top of the atmosphere. This is what is called the black body curve of radiation. And then because there are certain greenhouse gases in the atmosphere like water, methane, ozone, CO2, when you're down at the ground, this is actually what we see. And for a gas to be an efficient greenhouse gas, it has to absorb in this atmospheric window. And now I've put two of the anesthetic compounds on the same scale, so you can see that they do absorb in this atmospheric window. And I put, just for the sake of it, I put CFC11, which is one of the old chlorofluorocarbons. And that has I think, if I remember right, has a global warming potential of about 10,000. 10,000, yeah. And this is because it has this huge absorption right in the area where there's nothing else. So there's a code to give you the global warming potential. So you can calculate the instantaneous forcing. And when you want the global warming potential, like Philip already said, you have to integrate that over a certain time. Normally we do it over 100 years. And when we do that, we take the lifetime, we take the radiative efficiency, and we get some global warming potentials, and we can use them to put the anesthetic compounds on a more, how should I say this, on a scale that we can all relate to. So if you assume you take the 100-year global warming potential and you take the quantities and the mix of anesthetic agents that they use at the University of Michigan hospital, one procedure corresponds to about 22 kilos of CO2. And if we assume the 200 million procedures, you multiply that, you get 4.4 million tons of CO2. And then you might sit and wonder, is that a lot or is that nothing? And we're not going to have a vote, because some people will think it's a lot and some people will think it's nothing, and they are entitled to. But let's put it on a more user-friendly scale. So a power plant in the US emits typically 3.85 million tons of CO2, so anesthetics corresponds to one coal-fired power plant. Or if you're more into cars than coal-fired power plant, one US car, I normally give talks in the US, so that's why it's all US cars and stuff. So a typical US car emits 5 tons of CO2 per year, so it's 1 million cars. So if you think 1 million cars is a lot, then it's a lot. If you think it's not a lot, then it's not a lot. But that's what it is, in my mind. Okay, so you can relate to that. You can tell your patient, they can relate to it. What? I wouldn't recommend that. And then, we can also look at what is happening to the products of the atmosphere, and there's really no concern for those products. So to conclude, I think what we have done is we have established the atmospheric chemistry of anesthetics. The anesthetics are greenhouse gases with GWPs of these values that are exactly what Philip showed. And you can use those numbers to calculate the effect of what you do. And this is kind of my main message here, is that we provided the numbers and you use them with conscience and being deliberately honest like Philip was. And, if you want to put, at least with my knowledge, your contribution onto another scale, you can use one coal-fired power plant or 1 million passenger cars, and all the data is here for comparison. So thank you very much.